Good. So today we're going to start chapter 7, which is on alcohols. And alcohols generally also stopping off to discuss phenols and thiols to some extent. And alcohols are a really important functional group. I was thinking about this actually over the weekend. I think I even commented something similar to my 227 students this morning, which is alcohols are extremely common, exceedingly commonly used as starting materials in industrial synthesis of pretty much anything, with the possible exception of polymers. And I will admit polymers are un poco important. I wish we could do the chapter in polymers. There is one in your book. I just had to make choices. We are already having to get through a lot of material in just one term, and I have to sacrifice quite a bit on the depth, and adding a whole bunch more chapters would not have helped us in that regard. So it's a shame, since polymers are only one of the greatest technological advances of the 20th century, but we had to make some choices. But other than polymers, pretty much anything else you could come up with, any kind of pharmaceuticals at all, whether for humans or animals, anything that's involved, at least in terms of organic compounds that are involved in soil treatment or water treatment or anything like that, I would say if you at random picked out 100 organic syntheses from the current literature at any given time, I would bet you that probably all 100 of them, certainly 98 or 99 of them, would involve either an alcohol or an alkyl halide as the starting material. And as we'll learn in this chapter, alkyl halides can easily be made from alcohols, if that's what you need. So that's a couple days down the road. As before, and I'm not entirely sure why this is, we've got loads of time to cover chapter 7. I think I have 3 entire class days. So, and let me just make sure of that. I don't want to be lying to you. Yes, we have today, Monday, and Wednesday, and we're probably not going to need all of that. So what I might do is aim to finish chapter 7 in the middle of the class on Wednesday, and then take a little extra time on chapter 8 so that I don't have to rush through it all in one class day. Something like that is kind of how I foresee the next week. And then if I'm not wrong, our next exam is not this coming Monday, but the one after that, a week after this coming Monday. And as it says, that will not include chapter 8, as I always do. I like having that slop day in there, just in case something happens and we lose a class or something like that. That way we don't have to move the exam. But all that's in the syllabus, so you can check it out. It says in the syllabus what's going to be on the exam. So that's basically what's coming up. Anyway, I think we're already familiar with alcohols. The alcohol functional group, at least for what we call aliphatic alcohols, ALIPHATIC, is basically an alkyl substituted alcohol. And so for that, we need basically any alkane type carbon, sp3 hybridized carbon, attached to an OH group. And those confer, by the way, remember there is only one H in alcohol, please and thank you. I get alcohol all the time, it drives me crazy. Sometimes I think people do it because they know it drives me crazy. I guess I deserve it. But anyway, that's how we would define an aliphatic alcohol. Those in turn can be divided into different flavors. There is only one methyl alcohol, which you can call methyl alcohol, or you can call it methanol. Both names are fine. But there's only one way to attach an OH group to a methyl carbon. Usually we call this methanol. But methyl alcohol is not wrong. That's also fine. You can call it that. Everyone will know what you mean. Methanol, I'm not sure I mentioned this. Of course, it's the smallest possible alcohol as well. So forgive me if I did this already when we discussed alcohols in our discussion of functional groups, but did you just say only sp3 hybridized alcohol? Yep, that's right. So we need that carbon to be sp3 hybridized for it to be an aliphatic alcohol. That's exactly right. There are other kinds of alcohols, but they're not aliphatic alcohols, and we'll get to those. So methanol was a byproduct back in the Prohibition days when people were making booze pretty much in their backyards. And ethanol, of course, CH3CH2OH, that's the intoxicating component of adult beverages. But the way they were doing it, it wasn't a clean reaction, and they were getting some methanol as well in there. And ethanol, to be sure, is a teeny bit toxic. I mean, enough that it's possible to die of alcohol poisoning. You have to drink really a tremendous amount in order to do it. But methanol is really, really, really stupidly toxic. Like 15, 20 milliliters will kill you. So people were drinking this illicit booze and then they would die. So it was kind of bad in the Prohibition days. It didn't work out so well. So anyway, but there's only one methyl alcohol. By a primary alcohol, we mean an alcohol where there is one alkyl group attached to that OH attached carbon. So compounds of this type we call a primary alcohol. Just like you can have primary carbons, you know, it's the same terminology. And then, as you would guess, a secondary alcohol would have two alkyl groups attached to that carbon that bears the OH group and one hydrogen. So this type of alcohol would be a secondary alcohol. It's a Y. And then last but not least, oh, and by the way, of course, those R groups can be the same or different. They can also be connected into a ring. So that if this were like a cyclohexane ring with an OH on it, we'll look at that compound later. That would be a secondary alcohol also. That's perfectly allowed. And then last but not least, your tertiary alcohols will have three alkyl groups attached to that carbon. And these groups R1, R2, R3 can be all the same or all different, or two of the same and one different, whatever you like. That would be a tertiary alcohol. And I think you will see immediately that there can be no such thing as a quaternary alcohol. Because once you replace that OH with another alkyl group, well, you don't have an alcohol any longer. So those are the only four flavors of aliphatic alcohols there are. Other types of alcohols, at least the main other one that's important, and that we'll have something to say about in this chapter, is phenol and substituted phenols. So phenol itself is hydroxybenzene. And I think phenol was one of the monosubstituted aromatic compounds that you needed to memorize the name of back in chapter 4, because again, phenol shows up all the time. It's used for all kinds of things. Even in its own right, it was an antiseptic and still is sometimes used as an antiseptic. So it's a very important, industrially important compound. On the topic of polymers, phenol was actually involved in making the first commercially distributed polymer, which was Bakelite. This was way back. This was like 1920s. And so if you go to an antique shop, you'll find all sorts of little Bakelite items. Got to be careful with Bakelite. It's actually pretty fragile. It shatters pretty easily. Not quite as easily as glass, but it's pretty breakable. Good, so, and then you could imagine substituted phenols, where you have one or more other groups also on the aromatic ring, in addition to the OH group. And then, last but not least, you've got your thiols. Well, actually, maybe I'll do it the same way as we did with the aliphatic alcohols. So thiols are the sulfur derivative of alcohols. And again, we really need that carbon to be sp3 hybridized for a standard thiol. And what else was I going to say about that? I guess you could also imagine primary, secondary, tertiary thiols. That's not unheard of. You can use that same type of nomenclature. Thiols used to be called mercaptans. It's a funny word. Maybe I'll spell it out for you just in case you run across it so you don't get confused. MERCAPTAN. So mercaptan is the older word. No one really uses that, at least with any frequency any longer. Thiol's the more modern word and is the one that most people use when they describe sulfur compounds of this type. And as you might expect, thiols have some things in common with alcohols. Sulfur is, after all, right below oxygen in the periodic table. It's no surprise that you can get structures like this. There are also some pretty important differences. One of the main ones that you tend to notice up front is thiols stink to high heaven. And if any of you has ever smelled a skunk, then you know all about that. There's thiols and sulfides in skunk odor. You may also be aware of, if you've ever worked in like a student lab where they have those gas jets, you know, the natural gas. You know, if you leave a natural gas jet on for a little while, you'll start to smell something not at all pleasant. And that's because actually natural gas is odorless, but it's a safety issue. You know, if there's a gas leak, we need to know it before someone lights a match, and once again, people die. So it's a safety issue. And so that's why in natural gas that's distributed for that purpose, they have 0.5% or 1% of some thiol in there, just to make sure that we can detect it when there's a gas leak. So, so I think you want with that, and you've probably smelled that too. So I think you know all you need to know with that about how badly thiols smell. Yeah, I think that's all we really need to say about that. What should we say about the structure of alcohols? Well, it's very much like the structure of water. The oxygen in the OH group is going to be sp3 hybridized also, and you'll again get a bent geometry, if you will, around the oxygen, just as you do in water. But basically, the VSEPR shape of the oxygen in an alcohol will be tetrahedral, such that the oxygen's at the center of a regular tetrahedron, and the hydrogen on the OH and the carbon attached to the oxygen will be at 2 of the 4 corners of the tetrahedron. And at the other 2 corners of the tetrahedron, you'll find your 2 lone pairs on oxygen. So it's very similar structurally to water. You're just replacing one of the hydrogens in water with an alkyl group. And similar for thiols. One major difference between alcohols and thiols, whichever type of alcohol you're talking about here, is that alcohols experience quite a bit of hydrogen bonding. Remember, we've defined hydrogen bonding, and we said that hydrogen bonding occurs whenever you have effectively bonds to hydrogen from those 3 small electronegative elements: oxygen, nitrogen, fluorine. Fluorine almost doesn't count, because if you bond a hydrogen to fluorine, you've got HF and you're done. You can only form the 1 bond. But any compound that has OH bonds or NH bonds is subject to forming hydrogen bonds. And that's going to have implications for the properties of alcohols. It's why alcohols have very much higher boiling points than alkanes of similar molecular weight that don't undergo hydrogen bonding, for instance. So all of that same, all of those same things that, all those same types of arguments that we've previously made certainly apply here as well. And maybe for now, though I think I'll have more to say about it later. Phenol is technically an alcohol like any other. It has some similarities to aliphatic alcohols, but at the same time, phenol is special. And we'll have more to say about that later. But for now, I want to point out that phenol is a good deal more acidic than any aliphatic alcohol. I mean, it's a pretty shockingly large difference. It's by about 1 million or 10 million times, give or take, given the details. And we'll have more to say about that later and why that is exactly. But I think for that, that's enough by way of a brief introduction to all of these. Hopefully nothing too scary and unfamiliar. Questions so far then? Move this out of the way. Please register your attendance, by the way. I do have a reef pulling session for later. It will be over questions from the previous class on SN1 and SN2. So we'll get to that later. Good. Yeah, might as well move on then. Good, so in terms of naming alcohols, and we'll also say a few things about naming phenols, though we really already have in chapter 4. I'll just remind you of a couple of pointers. But naming alcohols is pretty straightforward. It's really not that much different from naming alkyl halides, which we've already gone over. But basically, your alcohols are going to have that OL, all ending. So I had some examples. I'm basically reading right off your class notes here. This compound, for instance, we could call that cyclohexanol. I think you probably could also call it cyclohexyl alcohol, but I don't know. Sounds a little fiddly. Everyone would know what you meant, but I think mostly we would call that cyclohexanol. Cyclohexane, cyclohexanol. Just like we went from methane to methanol, or ethane, ethanol. Cyclohexane, cyclohexanol. What else? 2-pentanol. Well, you would want a 5-carbon chain, and you'd put your OH on the second carbon from either end. It's the same way either way. And so just as if a bromine were here, you'd call that 2-bromopentane. We would call that 2-pentanol. So nothing too shocking. How often do we use phenol in comparison to ethanol? Well, both of those have quite a few industrial applications. I gave you one that I know about with phenol in making Bakelite. I know that it's used as a starting material lots of other ways. Also, phenol is an antiseptic in its own right. Ethanol is another thing, and there's, we make tons and tons and tons of that every day in America. And ethanol is used even as a gasoline additive, I think you guys are aware. And just as a building block, if we need to start with a 2-carbon building block, it's used a lot. But I would say they both are used quite a lot as starting materials, but probably for rather different types of compounds. And again, we'll get to the differences in properties of phenol as opposed to aliphatic alcohols. We'll save that for another day. Sometime next week, we'll get to that. And then we were also going to do benzyl alcohol. So that's a funny one. Remember this annoying term benzyl, benzylic. We've mentioned this before. It's really an annoying term because benzyl alcohol sounds like we ought to put the OH group right on the benzene ring. But we already know that's not benzyl alcohol, that's phenol. So benzyl alcohol is benzene ring CH2OH. That's about the worst CH2 I've ever drawn. I might even just give up and just write CH2OH. That might be clearer. So that's benzyl alcohol. So it's annoying. It's interesting coincidence. We went over this in my Chem 227 classes today, and I made the same whole spiel to them. It's unfortunate. It's a confusing term, benzyl and benzylic. Just remember the terms refer to the carbon that's next door to a benzene ring. Anytime you have a benzylic position or benzylic anything, it's the carbon attached to a benzene ring. It's not attached directly to the benzene ring. It's one carbon next door to the benzene ring. So it's a shame, it's a confusing term, but we're stuck with it. It was decided over 100 years ago, and none of us was around to complain at the time. So let's see. Yeah, I think those are good examples of alcohol names. You'll get to practice nomenclature also in the hour assignments. I think I have chapter 7 already set up to be due next week, a week from today. I'll certainly double check that. Now we've already done primary, secondary, tertiary alcohols. As for phenols, you can very easily run into a situation where I think you could have, I got asked this a lot also for the previous exam. I could very easily imagine situations where there could be 2 acceptable names. you know, do you call that, or I mean just CH3 over here? Is this going to be 3-methylphenol, or if you will, M-methylphenol? So 3 or meta, or are we going to call this 3-hydroxytoluene? Which is right? To be completely honest, I don't think I can choose between those two. I think they are equally correct. I have no preference at all one way or the other. What would be the geometry of phenol? You mean the geometry of the oxygen? Same, that would still be bent, just like in any other alcohol. So the oxygen's still sp3 hybridized. The carbon's sp2 though, because it's in a benzene ring. So the benzene ring part of the molecule is flat. That's all in the same plane. But the oxygen would still be bent. So I would say alcohol oxygens are always going to be sp3 hybridized, always. If it's an alcohol, same thing I would say with the sulfur and the thiol. Those will always be sp3 hybridized. They'll always be shaped as if they were at the center of a regular tetrahedron. And the carbon and the hydrogen attached to oxygen will be at 2 corners of the tetrahedron, and the 2 lone pairs in oxygen will be at the other 2 corners of the regular tetrahedron. So you'll see that makes it bent. Or your Gen Chem book might have said angular. Same difference. I see no real difference between those terms. Good. Let's see. I don't mean to embarrass myself, but I'm basically reading straight off your class notes and just making sure I don't miss anything. What is the region behind benzene ring being planar? Remember, cyclohexane is not planar, right? Cyclohexane is chair-shaped. And that's because it makes all the difference in the world whether these carbon atoms are sp3 hybridized as in a cyclohexane ring or sp2 hybridized. And it may make it easier to see if we draw the benzene ring the other way, which we certainly can. So remember, all of the carbons in benzene are sp2 hybridized. And as a result, they're all going to lie in the same plane. They have no choice. That's what sp2 hybridization means. It means that all of those 6 carbon atoms are trigonal planar or planar triangular. So although this carbon's sp3 and that oxygen's sp3, certainly all of the atoms in the benzene ring are planar. That's just part of what it means to be sp2 hybridized. And unfortunately, it's really not possible to discuss that without being circular in your reasoning at this level. You probably got that in your Gen Chem class, to say, why is an sp2 hybridized atom trigonal planar? Well, that's just how it works out. That's the shape it takes in order to be triangular. Well, why is it sp2 hybridized? Well, it has to be in order to be planar triangular. There's just no way you can do that in any other than a circular fashion unless you get into really heavy-duty quantum mechanics and start going absolutely nuts with molecular orbitals. It's just way beyond anything necessary to discuss here, and I actually, frankly, doubt I would be able to if I had to. Well, I guess if I had to, I'd work it out until I was able, but it's not appropriate to go that deeply into it. But yes, whenever you have an sp2 hybridized atom of any kind, not just carbon, it's always planar, always, no exceptions. But these carbons are sp3 hybridized, and I just do. And again, the way we know that is because each of those carbons has 4 single bonds. That by definition makes those carbons sp3 hybridized and therefore tetrahedral in shape. And you'd get the same thing there. Why is an sp3 atom tetrahedral? Well, because that's what it turns out to be when you take on that hybridization. Well, why is it a tetrahedral atom sp3 hybridized? Well, it has to be, or it can't be tetrahedral. You know, you just wind up being circular on it. And probably a lot of Gen Chem professors don't even pretend otherwise at this point. To go beyond that is very, very high level stuff. And I don't think anything we need concern ourselves with here. Good. Let me just make sure I'm going to do another aromatic one, but any questions on that? So I guess my point with a compound like this is I really do think both names are equally correct. I couldn't even give you 5149 on this. I think they're exactly equally correct. I think they're both that they're both completely acceptable. I don't know that I could give you a list of rules or a list of things you need to remember for when you would use one and when you would use the other. There does come a point where one might be more convenient than the other. I don't know if you started putting a whole bunch of different groups on there. I mean, something like that would be very weird to call 2-hydroxy-3,5-dichlorochlorobenzene. I think you'll agree that just sounds silly. I think it makes a lot more sense to call this 2,4,6-trichlorotoluene. And the reason for 2, 4, and 6 is the one carbon is assumed to be the one with the OH on it because we're calling it a toluene. So we're numbering the carbons something like this. I think that name makes a lot more sense than the other one. I really do think common sense will go a long way for you here. Did I say toluene trichlorophenol? Well, you'll be able to look at YouTube, unless I delete it, and see whether I said trichlorotoluene. But I would call that 2,4,6-trichlorophenol. I think that makes a ton more sense than, 2-hydroxy-3,5-dichlorochlorobenzene. That just seems silly. I think that name makes a lot more sense. Good, so those are just some examples of how to name aromatic alcohols, phenols. Let's see, I think we've, I already mentioned about hydrogen bonding. I'll just make sure that I didn't miss anything. And yeah, I think I've already said that about hydrogen bonding. So with that, I think we're pretty well through of most of 7.1 through 7.4. And that's really all I think I was supposed to do today. So I do have a reef session. And if we have time after that, I can make up some questions about alcohols or SN1 and SN2, and we can work through them. But beyond that, I don't see the need to push this any further, especially on a Friday. To be completely honest, I noticed I got a phone call while I was up here that might be important. So I'm not going to end class now. Let's do our reef session. And then if there's time, I can make up some problems and work through them with you guys. But if we wind up getting out a few minutes early, if you guys don't object, I won't object. And I somehow doubt you guys will object. Good. Any questions before we do our reef session then? Let's see. All right, well, let me move on to sharing my PowerPoint. And again, this is going to refer to stuff from chapter 6 on nucleophilic substitution. And as usual, you know the drill by now. I've not put in the answers, so we don't have that problem. I'll put them in later. So my first question, hopefully all those of you in chat can see it also. Which of the following pairs of reagents would likeliest lead to an SN2 reaction? And here's one pair, here's another, here's another, here's another, and here's another. And I would put it to you that that's unambiguous. There's one of those 5 is definitely the best choice. Good, we'll call it there. Well, what leads to the best possible success of an SN1 reaction? Well, we said that in an SN1 reaction, for best results, you want your substrate to be tertiary. That's because the first step and the slow step, the rate determining step in an SN1 reaction is just loss of the leaving group to give a carbocation. And that's your best chance of that is if the substrate is tertiary. Again, secondary is your intermediate case. Secondary substrates might react a little bit in an SN2 fashion as well, SN1 fashion as well. It's not unheard of for secondary substrates to do both. Not that it really matters much practically because you'd get the same thing either way, but that's certainly one thing that you want. So that narrows it down to C and E. And the other thing we want for best results in an SN1 reaction, it's most common for the solvent and the nucleophile to be the same thing. And actually, now that you mention it, that one is in your notes. That is I should have used something else like methanol to try to throw you guys off. Oh well, but I didn't. So yes, I think E is the best answer for this one. What? Well, sorry, I think E is the best answer. So that's basically it. Can we say water is also a nucleophile? Oh yes, in this case it's both. It's both the solvent and a nucleophile. Still threw them off, oh no, sorry. Anyway, I haven't written the answers in yet, but I will. I'll get all of these uploaded this weekend, as well as update all of your reef scores. As I said, I'm about 2 weeks behind, but I'll get all that updated. And also figure out the curve in the exam and figure out your estimated class grades at this point in the term. So all that will be happening one way or the other over the weekend. And we're at, gee, I have 6 minutes left. I know you guys probably don't. 6 minutes is, I would be a little bit embarrassed to let you go this early. What do we do before chapter 6? Chapter 15. That was way long ago. We did a cry. No. Because I trying to think of a lipids question. We had a lipids reef session not too many days ago. So I think we don't need to go there so much. Let's see if I can come up with, let's make up an SN2 question. Just talk for a few, no. Let's see here. Let's suppose, no, don't sit there in silence. Let me at least give you something to do. Let's suppose that we had this secondary alkyl bromide as the pure, let me see, S enantiomer. Try your cats, no. Let's see. So let's, and again, I wouldn't expect you to be able to tell me that it's S, but it is S. I just figured it out and you can believe me. Let's say that we did an SN2 reaction on this. And even though it's secondary, let's say it works. So let's treat this with, what nucleophile do we want? How about potassium ethoxide? So remember what we mean by an alkali metal salt. Meow and grr, well, or hiss in the case of Bella. I hear her hissing at Barnaby all the time. Doesn't matter, doesn't faze him one bit. Why should it? She has no teeth. Anyway, I made that look like an I, didn't I? I'm just gonna give up and try that again. Hey, no fair drawing in my thing here. Good. So I'll even give you a hint. Remember that means our nucleophile is the ethoxide ion, CH3CH2O minus. So here, give me the SN2 product and make mention of the, does there is a list because for lack of teeth? I don't know. I think they make it from their throat, not like through their teeth. Good. So, right. So give me the SN2 product, being careful with the stereochemistry. Even since it's the end of class, remember we said that in an SN2 reaction, we get complete inversion of stereochemistry. So give me that. And then let's also do an SN1 reaction. Here we'll just take ethanol. Ethanol will be our solvent and our nucleophile. I have a sinking feeling that this is terribly similar to our next reef pulling session, though I can always change that and come up with something else. Here, I'd like you to give me the SN1 product, and please give me the final product, the stable, neutral product that you would get from an SN1 reaction, and what can we expect in terms of, I've only left you 2 minutes, but what can we expect in terms of stereochemistry? So I'll let you dwell on that until it says 3:44. Hey, people still drawing on my board. What now? Oh, I don't know. They're actually able to do it. Your answer is B. Good try, but I don't think B is going to work. So that's 344. I don't want to keep you past the time. So our SN2 product, remember that in SN2 reactions, we invert the stereochemistry at any chiral carbon. So that's going to make this go to the S enantiomer, which will mean that my hydrogen that was pointing back will now point forward. And remember that it's a substitution reaction. So we replace the leaving group with whatever our nucleophile is. And that's what's going to go right here, an ethoxy group. And I would expect that you would get the pure R enantiomer over here. You get 100% inversion of configuration. Meanwhile, with the SN1 process, since this goes through a planar intermediate, a carbocation, that means your nucleophile can come in from either side and will come in from either side. And so you will get a mixture of both. So I'm just going to draw this as a straight line bond. First step, you'll get the secondary carbocation, and then you'll get the species that has the proton still attached in a plus charge, and then a solvent molecule will come in and pick off that proton and give you, in fact, the same product, but you would get both R and S. Because in an SN1 reaction, you lose all stereochemistry. So even if you start with a pure stereoisomer, that's gone at the end of the reaction. What had been a chiral carbon with just one pure stereochemistry, you wind up getting both over an SN1 reaction. So take a look at that. That's something we covered in the last class, but I thought that'd be pretty good to go over. Other than that, I'm out of time, so I will try my very best to get all that stuff done over the weekend. Other than that, have a great weekend. We'll see you Monday.